The sun rises over a quiet airstrip in Africa, casting a golden hue across a scene that will soon make history. On the tarmac sits a sleek aircraft, unlike anything seen before. No fuel lines, no charging stations, no external power sources. And yet, today it is poised to defy everything conventional aviation has taught us. This is Africa's first self-powered aircraft, and its first flight is about to change the way the world thinks about energy, flight, and innovation. Engineers, scientists, and observers gather around, eyes fixed, cameras rolling. Skepticism hangs in the air like morning fog. Some have dismissed this as impossible, a dream too ambitious to ever lift off. Others are cautiously hopeful, watching for signs that this could be a historic breakthrough. The pilot climbs into the cockpit, the canopy sliding shut with a quiet hum. A soft glow from within the aircraft's internal systems pulses rhythmically, signaling readiness. There's no engine roar, no conventional startup procedure, just a steady, almost ethereal hum. Instruments indicate energy levels that should not exist in any known aircraft. Then, slowly, the plane begins to roll. Its wheels glide over the runway with effortless grace. Observers hold their breath as it accelerates, picking up speed without consuming any conventional fuel. Meters, thermal cameras, and telemetry systems record data that defy expectations: stable energy outputs, negligible heat loss, and efficiency levels previously thought unattainable. And then, the impossible happens. The aircraft lifts off. Smoothly, elegantly, silently, hovering for a moment before accelerating into the sky, climbing higher and higher. Gasps ripple through the crowd. Engineers double-check instruments. Data confirms what their eyes are witnessing. Africa's first self-powered aircraft is airborne, and it is fully functional. As it maneuvers gracefully above the airstrip, executing precise turns and ascents, patterns emerge in the data that are as shocking as the flight itself. The aircraft isn't just flying, it's self-regulating. Minor disturbances, such as gusts of wind, are compensated for instantly. Energy distribution is perfectly balanced. The system adapts in real time, maintaining stability with a sophistication no conventional aircraft can match. Observers begin to whisper, if one aircraft can achieve this, what happens when a fleet is deployed? Could Africa become the center of a new era in self-powered aviation? Could this technology redefine energy usage, logistics, and transportation across the continent, and eventually the world? Every eye is on the aircraft as it continues its historic flight. This is no longer just a test. It is a statement, a challenge, a glimpse into a future that many thought impossible. And yet, even as cameras capture every angle, even as telemetry data is logged meticulously, one question hangs over the airfield, unspoken but unavoidable. If one self-powered aircraft can achieve this level of performance, what will happen when the technology is scaled? As the aircraft continues its flight, the focus in the control tent shifts from astonishment to strategic analysis. Every reading, every fluctuation, every micro-adjustment is recorded, analyzed, and cross-checked. This is not a demonstration anymore. It is a live experiment unfolding before the eyes of experts who had long considered such technology impossible. The team begins running simulations in parallel, exploring scenarios that were previously theoretical: high-altitude endurance flights, extended distances across the continent, operations under extreme weather conditions. Each scenario tests the limits of the aircraft's self-powered system, and every new calculation reinforces what is already clear. The technology is behaving in ways that conventional physics and engineering models cannot fully predict. Questions start circulating quietly among the observers. Could a fleet of these aircraft operate in coordination? Could multiple planes share energy dynamically, compensating for each other during flight? Could emergent patterns appear that would further enhance efficiency or stability? The possibilities are staggering, and each question raises equally profound challenges. Meanwhile, subtle tests begin in real time. Minor disturbances are introduced deliberately. Sudden gusts of wind, brief load imbalances, simulated mechanical strain. In every case, the aircraft adapts instantly, redistributing energy and maintaining stability. Observers realize that this is not merely self-powered flight. It is self-optimizing flight, a system that corrects and balances itself in real time without human intervention. The implications expand rapidly in everyone's minds. If a single aircraft can maintain energy autonomy and stability, remote regions without fuel infrastructure could suddenly become accessible. Humanitarian aid, medical supply delivery, and disaster relief could be transformed overnight. Aviation logistics could operate with far less dependence on fuel, infrastructure, or maintenance constraints. Even the skeptics begin to reconsider. What was once dismissed as fantasy is now being documented meticulously. Telemetry, thermal imaging, energy flow analysis, all of it points to a reality that cannot be ignored. Maxwell's invention is not just an aircraft. It is a prototype for a potentially transformative class of technology. As the flight progresses, attention turns to endurance. The aircraft remains stable, efficient, and responsive for a duration far exceeding initial expectations. Thermal readings remain low. Energy distribution continues to adjust in real time. Each minute in the sky reinforces the possibility that this is more than an isolated breakthrough. It is the foundation of a new paradigm. And yet, even in this historic moment, one question looms larger than any data point, any observation, or any calculation. If Africa's first self-powered aircraft can perform at this level, what will happen when the technology is scaled, deployed in fleets, integrated into global transportation networks, and subjected to the unpredictable variables of the real world? Back at the airfield, as the aircraft completes another flawless maneuver, the discussion shifts to replication and scaling. Observers realize that a single successful flight proves concept, but it does not guarantee reliability under broader conditions. To truly validate the technology, multiple aircraft must be tested, independently verified, and subjected to varied environments, payloads, and operational stresses. Plans for the next phase begin quietly. High-altitude flights, cross-country endurance tests, and flights under extreme weather conditions are scheduled. Every variable is considered: temperature fluctuations, wind shear, equipment redundancy, and even potential interference from external energy sources. Each test will push the aircraft and the underlying technology further, revealing strengths and exposing any unforeseen weaknesses. Meanwhile, engineers start theorizing about networked operations. If one aircraft can maintain energy autonomy, what happens when multiple aircraft operate in formation? Could they exchange energy dynamically? Could emergent behaviors appear, optimizing performance across a fleet in real time? The thought excites and unnerves everyone. A single aircraft challenges current engineering, but a fleet could redefine global aviation. Observers from private aerospace firms, research institutions, and government agencies began inquiring discreetly. Skeptics who laughed before are now asking questions about independent verification, peer-reviewed documentation, and controlled demonstrations. The invention has shifted from curiosity to potential disruption, quietly attracting attention at the highest levels. In the lab, minor disturbances continue to be introduced intentionally: sudden gusts, weight imbalances, simulated turbulence. Each time, the aircraft compensates automatically, stabilizing in real time without external input. The system's self-optimizing behavior becomes undeniable, revealing a level of adaptability that conventional flight systems cannot achieve. At the same time, telemetry data shows something unprecedented. The longer the aircraft operates, the more stable its energy systems become. Efficiency doesn't degrade, it improves slightly. The aircraft seems to learn from operation, adjusting its internal dynamics to maintain optimal performance. Observers realize that this is not just a machine. It is a self-regulating system operating at the edge of what is technically possible. Outside the lab, the implications begin to take shape. Remote regions, previously inaccessible due to fuel limitations, could now be reached. Humanitarian aid, disaster relief, and medical supply delivery could be reimagined. Aviation logistics, both commercial and private, could operate without dependence on fuel or traditional infrastructure. And yet, despite all the data, all the observations, and all the calculations, one ultimate question remains. If Africa's first self-powered aircraft can operate autonomously at this level, what will happen when the technology is scaled globally? As night falls over the airfield, the aircraft rests quietly, its subtle glow a reminder of what has been achieved and what remains to be tested. Inside the control tent, the team continues analyzing every reading, replaying every second of flight footage, and cross-referencing telemetry with environmental data. Nothing is left to chance. Every anomaly, every micro-adjustment is meticulously logged for review. Plans for extended endurance flights are underway. Engineers discuss multi-day tests, longer distances, and flights under extreme weather conditions. Every variable, altitude, payload, temperature, wind, and even potential electromagnetic interference, is mapped and simulated. Each scenario aims to uncover the limits of the system, but also to reveal the immense potential hidden within its self-powered design. The conversation soon shifts to fleet coordination. If one aircraft can maintain energy autonomy, could multiple aircraft operate together, dynamically adjusting their energy flows in real time? Could they optimize flight paths collectively, reducing inefficiencies in ways no conventional system could achieve? The very idea of a self-regulating fleet sparks both excitement and caution among the observers. Meanwhile, private aerospace firms and research institutions quietly reach out, requesting observation opportunities. Even skeptics who once dismissed the concept as fantasy now seek access, data, and verification. Maxwell's invention has quietly become a technology of interest, a potential disruptor with global implications. The aircraft undergoes repeated testing. Simulated turbulence, abrupt load changes, and environmental stressors are introduced. Each time, the aircraft responds instantaneously, redistributing energy internally to maintain stability. Observers realize that this is no ordinary flight system. It is self-optimizing, adaptive, and capable of managing complexity beyond conventional engineering models. Telemetry reveals something even more astonishing. The longer the aircraft operates, the more efficient it becomes. Energy flows stabilize, minor fluctuations are corrected automatically, and the system appears to learn from its environment. It's as if the aircraft itself is refining its performance with each moment in the air. Outside the lab, the implications become clear. Remote regions previously unreachable due to fuel scarcity could now be accessed. Emergency relief, medical supply delivery, and disaster response could be transformed. Commercial aviation could be reimagined, freeing fleets from dependence on traditional fuel infrastructure. Yet, even with all the success, one ultimate question remains unanswered. If one self-powered aircraft can perform at this unprecedented level, what happens when the technology is scaled, when fleets operate globally, when real-world conditions are no longer controlled, and when society begins to rely on systems that defy conventional energy paradigms? As dawn breaks over the airfield, preparations for the next phase begin in earnest. The single historic flight has proven the concept, but now the focus shifts to endurance, scalability, and real-world validation. Engineers and observers move methodically, coordinating equipment, recalibrating sensors, and planning routes that will push the aircraft beyond anything previously attempted. The aircraft is inspected meticulously. Every energy cell, every circuit, every control interface is verified. Unlike conventional planes, there is no fuel system to refuel, no battery packs to swap, only the self-contained energy system that has so far defied expectations. Engineers discuss theoretical limits, but with each passing test, they realize that much of what they believed about flight efficiency, energy consumption, and adaptive control may need to be rewritten. Extended flight tests begin. The aircraft ascends to higher altitudes, traverses longer distances, and navigates varying wind conditions. Observers track energy redistribution in real time, noting patterns that suggest the system adapts dynamically to environmental stresses. Unlike traditional aircraft, efficiency does not degrade over time. Instead, metrics indicate a subtle improvement in energy stability as the flight progresses. Attention inevitably turns to fleet deployment. If one aircraft can self-regulate and maintain energy autonomy, what happens when multiple units are coordinated? Could fleets operate autonomously, exchanging energy, optimizing routes, and adapting collectively to challenges? The questions are no longer theoretical, they are engineering imperatives, demanding careful simulation and cautious experimentation. Interest outside the lab intensifies. Aerospace companies, research institutions, and government agencies quietly request observation. Even the most skeptical engineers are compelled to reconsider. This is not a concept, it is operational technology with transformative potential. The implications for global aviation, logistics, and remote infrastructure are staggering. Intentional disturbances are introduced during extended flights, abrupt load shifts, turbulence, and unexpected environmental variations. Each time, the aircraft compensates instantly, maintaining stability and optimizing internal energy flow. Observers note the system's remarkable resilience. It behaves less like a machine and more like a living network, adapting in real time without human intervention. By now, it is clear, this is not merely a technological breakthrough, it is a paradigm shift. Remote regions, disaster relief, medical supply routes, and commercial aviation could all be transformed if this system can be scaled safely. Yet, even with all these successes, one critical question remains unanswered. If Africa's self-powered aircraft can operate autonomously at this level, what happens when the technology is deployed on a global scale, under uncontrolled conditions, and subjected to the unpredictable realities of the world? As the aircraft glides back to the airfield, its historic flight complete, the weight of what has been achieved settles over everyone present. Africa has proven that self-powered flight is possible, that energy autonomy in aviation is no longer just a dream. Yet, this is only the beginning. The true challenge lies ahead, scaling the technology, testing it under real-world conditions, and exploring the vast potential it represents. What started as a single flight now hints at a future where aviation, logistics, and energy use may be fundamentally transformed. The world has witnessed history in motion, and one undeniable truth remains: the era of self-powered flight has begun. The skies and the future will never be the same.